Welcome to my talk. This is called Protected Encryption Keys with Azure Key Vault. And, ooh, what's happened there? Oh, is anyone from IT in the room? Ah, there we go. Okay, so I'm an independent consultant, software developer, and also Pluralsight author, so I've been working with them for the last 4 years, and I'm now working on my 14th course. And also do some consultancy work for a blockchain consultancy in the UK called Block3, where we go in and help companies assess whether blockchains are actually going to be useful for them or not. So a rough agenda of what we're going to talk about today. So we're going to talk a little bit about data breaches. We're going to talk about a very quick high-level cryptography overview, just so everyone's on the same level. Then we're going to talk about traditional key management options. And then from there, we're going to introduce Azure Key Vault. And then we're going to cover sort of different patterns and practices that you can use with Azure Key Vault. So first of all, let's talk about data breaches. So the slide on the screen here is from a website called breachlevelindex.com, and they're a security consultancy in the US. And the reason I like to show this slide is because it shows a really good dashboard of some statistics. So at the top there, we can see that since 2013, and I think this is US-based, there's been 9.7 billion records stolen. Now, that number doesn't really shock me anymore, because data breaches happen every day and they seem to be getting worse. The number that does shock me is the bit underneath there where it says 4% of breaches were classed as secure breaches. And what they mean by that is whether the data was actually encrypted. So traditionally, you get a data breach, data gets leaked onto the internet, and lots of people's personal information is freely available in those files. But to be a secure data breach, it means that important information is actually encrypted. But only 4% of those were actually secure data breaches, which is quite shocking. Some other interesting stats on there as well. So this is about 5 million records a day are being breached, which is about 210,000 every hour, or 3,500 every minute, or 58 a second. So it just goes to show just how bad this problem is. Now, data breaches have lots of different effects on both customers and consumers. So for a company, it can lead to a loss of reputation, which is quite catastrophic for any company, which then leads to a loss of sales. It can lead to your customers switching to competitors. And it can also lead to class action lawsuits and legal action from customers or other companies. Another thing to bear in mind is compliance costs. So if you lose card data, then you'll fall foul of PCI DSS legislation, HIPAA in America, and of course GDPR, which comes into effect on Friday. So it also affects consumers badly as well. So they're having their personal data lost, so their names, addresses, email addresses, phone numbers, or any kind of preferences for the sites that they're on are being leaked onto the internet. And this can result in ID theft, impersonation, loss of financial data if someone gets hold of your banking details or card details. And it can also compromise your transaction history. So if you've purchased things on certain websites which you don't really want anyone else to know about, that data could potentially get leaked. But the sad state of fact is that data breaches are inevitable, and I think this kind of requires a mind shift change in how we think about data breaches. You're never going to stop them, so it's a case of not if, but when it's going to happen to you. So you kind of need to get into the mindset of preparing for a data breach, because it could happen to anyone. I mean, just because you're a small company as well doesn't mean you're too small to be affected. It actually means you're an easier target. Now, traditionally, we spend a lot of money focusing on perimeter security, so firewalls, intrusion detection systems, and those are all good things to do, certainly. But what if you have someone who's a malicious insider in your company? So someone from IT operations who has access to production databases, rogue developers. So don't just focus on the perimeter. So really what we want to focus on then is an extra level of encryption. So most databases these days let you do data encryption at rest. SQL Server on Azure lets you do it, Cosmos DB. And that's all well and good, but if you have an IT operations person who's got access to your database and they effectively do a select star across all your tables and dump it into a CSV file, the data at rest isn't really going to help you. So what you want to do is you can go one level on, which is what we're going to talk about today, which is actually doing record or row level encryption. And that's going to be for all things that you class as critical, so personal identifiable information, anything that relates data back to a living person, credit cards, or just anything generally sensitive. And it's quite interesting that we're doing the talk this week because this comes into effect on Friday. So GDPR has massive consequences for everyone. So I did this talk, or a version of this talk, in the US a couple of weeks ago. And I actually spoke to a few people there who thought, this doesn't really affect us, we're in the US. But if you have any European customers, either citizens or companies, then GDPR affects you. So that's kind of the intro. So let's just do a very quick cryptographic overview, just so everyone's kind of familiar with all the terms we're going to use today. So cryptography is generally split down into 4 core pillars. So we have confidentiality, which is what everyone typically thinks of with encryption. We have integrity, which is how you want to detect if data has been changed or corrupted in transit. We have authentication, where you want to prove that someone has actually produced a piece of data or sent a piece of data. And then finally, we have non-repudiation, which is kind of, the best way of thinking of this is kind of like a contract. So if you produce a contract with someone, you want to be able to prove that you was the person who signed that contract. Now in .NET, or .NET Framework and .NET Core 2.0 and above, these are the typical functions that we're going to use. So we're going to use AES and RSA for confidentiality. We can use SHA-256 or SHA-5112 for integrity. We can use hash message authentication codes, or HMACs, which can be based on SHA-256 or SHA-512. And then we've also got digital signatures that we can use in .NET. So these are some of the things that we're going to play around with in some of the demos. Then when you get each of those primitives and you start mixing them together to form larger protocols, this is generally referred to as hybrid encryption. And this is what we're going to be looking at today. So for confidentiality, encryption is generally split down into 2 areas. We have symmetric encryption and asymmetric encryption. So in .NET, that means things like AES, DES, and triple DES. I include DES and triple DES on there because even though you don't really want to use it for a new system, if you work for a large legacy company, you may have to interact with systems to still use it. So I was in that situation working for a couple of banks in the UK. Our core banking platform used triple DES behind the scenes. Now the way symmetric encryption works is you have one key, and that key is used to both encrypt and decrypt your data, hence why it's called symmetric. On the flip side of that, we have what's called asymmetric encryption. So typically we use things like RSA or elliptic curve for that. And with this system, the keys are split into 2. So you have a public key and a private key. And those keys are mathematically linked. It's all based around modulus arithmetic, which we're not going to go into. But the private key is a key that you have to keep private, hence the name. So you don't want anyone else to have access to that key. You want to protect it. And a public key anyone can have. And typically the way this works is you use the public key to encrypt your data, and then the person's private key, which is secret, to decrypt the data. Now, the good thing with things like AES and DES is they're very fast, so they're algorithmic by nature. They take data, split them down into chunks, and then perform encryption operations, which are the things that computers are very good at. But the problem with it is keys, or symmetric keys, are very hard to share between 2 people. So if I wanted to send an encryption key to Scott, how would I do it? Would I email it to him? Probably not a good idea. Do I want to stick it on a USB stick and throw it at him? Whilst it's fun, it's probably not a good idea. So getting that key to someone is actually very difficult. On the flip side, you've got things like RSA, which, because they're based around modulus arithmetic, they're actually very slow in how they work. And there's certain limitations as well. So if you've got a 2048-bit RSA key, you can't encrypt a chunk of data that's larger than the size of the key. So that's one of the downsides. But the keys are easy to share because you've got the split key idea, so the public key can go to anyone and the private key remains secret. So in .NET, to do these different operations, we'd use the classes like AES Crypto Service Provider and RSA Crypto Service Provider. So these are things that we're going to be playing around with in a moment. So let's look at key management options. There's lots of different ways of managing keys, some good, some bad. The first one, whilst it is a bit of a joke, I have seen companies that do this, is storing encryption keys in files on servers in a folder. So I hope no one actually does that, but I've actually worked for 2 companies where when I've got there, you go onto one of the file servers, and on D drive, there's a folder called keys with 2 XML files in there. So don't do that, it's very bad. But typically what we generally have is things like X509 certificates that we can install on servers. Now these have been around for a long time, they're kind of well known and trusted. And they allow you to do things like proving who's issued the certificate or who it's been issued to, public key verification. And generally, you get these certificates, you install them directly onto servers, and they're quite a robust mechanism. There's lots of benefits in that it's minimal impact for the end user. Typically, most systems will install these things directly, or you have an operations team that will manage them. You don't generally require any additional hardware, so Windows has a key store built into it, which is quite common to use. And they're easy to manage, and they're pretty much supported by everything. But there's one step that we can go to that's better than using certificates, and that's to use something called a hardware security module. So I've got some examples of them on the screen here. And typically, they're 1 or 2U rack-mounted appliances that will go into your data center. And a good thing with these types of devices is they're generally tamper-proof, both from a software perspective and a hardware perspective. So if you try and remove the case on one of these, it will wipe the machine. If you manage to get through the case, and there's probably things like temperature sensors and light sensors inside, and all of the chips are covered in sort of very durable resins, you can't actually get through to the chips. So these are very good. Now, typically you'd have 2 of them or more, because you don't just want to have a single key vault, and if that goes, or a single HSM, and if that breaks, you don't want to lose all your keys. So generally you might have them replicated across different sites. And you can also use them to store certificates as well. But the problem with these is they're very expensive. So unless you work for a very large organization with higher budgets, buying HSMs has been quite cost prohibitive. So one company I worked at, we spent about 80,000 UK pounds on a set of HSMs, which is kind of out of reach of a lot of small companies. But this is where Microsoft comes in with Azure Key Vault. So cost is no longer an issue, which is great. So Azure Key Vault is designed to safeguard encryption keys and certificates in the cloud. And what they've done is they've filled their data centers up with lots of these devices. These are the N-Shield hardware by Thales. I'm not quite sure how much these cost, because when you go to the website, it just says contact us for information, which means expensive. But Microsoft has taken the hit on this, and they've put lots of them in their data centers, and they've put an abstraction on top of it, which we can use. Now, there's different ways in which you can use it, and you get charged differently based on that. We'll look at some example costs in a moment. But you can put it into what's called hardware or software mode. So on both modes, you have master signing keys that are stored on hardware, so you're getting the benefit of the hardware. But if you're in software mode, if any encryption or decryption operations that you do in Azure Key Vault are actually done on virtual machines behind the scenes, whereas if you're in hardware mode, which costs more money, then the encryption and decryption is done actually on the appliance itself. And there's kind of benefits of both. So you might want to use the software versions in your dev and test environments to keep your costs down, and then the full hardware version in production. So let's look at some example costs. So for non-key operations, so you've got 2 different service plans. You've got standard and premium. So if you're doing anything with secrets, and we'll go into details on secrets later, it's going to cost you about 3 cents, US cents, per 10,000 operations across both service plans. Certificates will cost you $4 per renewal request. And then any other operation is 3 cents per 10,000 operations. For software key operations, by default, you get RSA 2048-bit keys. And again, that costs you 3 cents per 10,000 operations. But currently, they've got on trial at the moment 3072 and 4096-bit keys. Currently, these are free while it's in preview, so I'm not actually sure what the final cost for those will be. Now, if you're using the Azure Key Vault in hardware mode, you can only do this in a premium service plan. So that will be, for standard keys, that's $1 per key, and 3 cents per 10,000 operations. Or if you're using the higher keys, and it goes on a tiered pricing model from £5 per key, sort of down, the more keys you have. So some of the tricks I'm going to show you in a moment, we're going to basically get a lot of these costs down to virtually nothing, which is good. One key thing to say about putting keys in Key Vault is that once you create your encryption key there, it never comes out again. So you can never actually pull your key back and have a look at it. You can technically do a backup of that key, but it's encrypted first before it's sent to you. So once the keys go in, they don't come out. Now, setting up Key Vault is quite straightforward. Unfortunately, we don't have time to go through the install process because we've only got a short amount of time today. But the documentation from Microsoft is actually very good and walks you through the process. So there's a link to it there. Or if you just Google for Key Vault setup instructions, it'll take you through it. But effectively, the easiest way to do it is with PowerShell. So you create or reuse a resource group. You create your key, specifying the region and whether you want a hardware or software version of it. And then at that point, you can create and delete and modify your keys and upload certificates. Once it's been created, you just access it in Azure via the normal bladed interface that you're probably all familiar with. For us to programmatically access Key Vault, because a lot of Microsoft services all use Key Vault behind the scenes, but what we want to do is we want to access it from our code so we can sort of leverage it ourselves. To do that, you first need to go into Azure Active Directory, which sounds horrible, but it's not actually that bad. And you need to register your application and set up an app ID and shared secret. So those instructions that I pointed to earlier tells you how to do all of that. Now, we talked a bit about secrets as well. So there's two different types of data, apart from certificates, that we can store in the Key Vault. So we've got our encryption keys, which we're going to use for doing encryption operations later. And we've got something called secrets. And what a secret is it's a 25K or up to 25K blob of text that you can send to the Key Vault, and it'll encrypt it and store it for you. So typically, you might use this for things like connection strings, database passwords, anything that you don't really want anyone else to see. So you can kind of think of it as a very simple key value pair store that's encrypted. So all the code we're going to look at today is freely available on GitHub. I've released it under an MIT license, so you can do what you want with it. But if it breaks, it's not my fault. So everything I've got here, you can just take it and use it in your code. So the way you get access to Key Vault is you need to install a NuGet package. It works under .NET Core 2 and .NET Standard 2 and above, which is great, which is hence why I'm going to present from a Mac. There are, yeah. So you can get JavaScript bindings, Node bindings, or it all works behind a REST interface, so you can just do web API calls if you want. I'm a .NET guy. Ooh. Okay, so let's do a quick Hello World demo. Okay. So this is the Hello World of Azure Key Vault. Hopefully the internet connection is going to be good to me. So I've got a const string here, so I'm setting up a key name. That key name can be anything. I've just called it Stephen Hawkes' key, because it's mine. And then what I'm going to do is I'm going to make a call to the Azure Key Vault, and that's going to create the key over in a UK data center currently. Oh, it's taken a while. It doesn't normally take this long. I've been having lots of Wi-Fi problems this morning. Right, there we go. So that gives us a key ID back. Now that key ID is virtually unreadable on my screen. Can you see it there? Okay, so it gives you a URI back to your key on the Key Vault, and that's what you need to specify when you do an encrypt or decrypt operation. So I've got a string here with hello world in there. So first of all, I'm going to encrypt it. So this will be doing the encryption using RSA on the Key Vault itself. So I specify the key ID. I turn my string into a byte array, because everything has to be byte arrays when you send it across. And I've now received an array back with all my encrypted data in there. So now I can decrypt it straight away, convert those byte arrays into strings. So there we can see our encrypted text. Well, it's quite hard to read up there. And then we can see where I've decrypted it. It says hello world again. And then just for being tidy, I'm going to delete my key. So that's hello world on a Key Vault. Okay. Oops. So now we've got access to the Key Vault, and we've done our hello world, which is a very simple encrypt and decrypt operation. Let's look at some different patterns and practices that you can do. So the Key Vault effectively gives us some simple operations. We can create and remove keys. We can do encryption and decryption operations. We can set and retrieve secrets. And we can also sign and verify digital signatures. So those are the kind of base simple operations. But what they give us is something quite powerful that we can build on top of that. So we're going to talk about 6 different items here. So we've got multiple environments, configuration of secrets, local key wrapping, key versioning, password protection, and digital signing. So typically when you're working on a product in your team, you'll have test infrastructure set up. So one of the things you want to make sure you don't do is use a shared key environment across all of your environments. So you don't want to use the same Key Vault for development, test, and production, because you have to treat production as if it's, secret, it's special. So what you can do instead, and you can do something like this, where you have one shared key vault instance for your test environments, which could be a software-based key vault, and then have a hardware-based key vault for production. That's one way of doing it. I've seen companies do that. Or if you script all your deployments and environments, then you could just have a separate key vault per environment. So it's very important that you never share any of your keys or secrets from production into any other environment. That's kind of absolutely paramount. Okay, so configuration of secrets. So I've already mentioned that secrets are effectively up to 25K blobs of text, which you can treat as like a key value pair store. Now these are stored encrypted in the HSM with a master key inside the HSM, so you don't specify the key for this, Azure Key Vault does it for you. So you might want to store things like connection strings, API keys, Redis cache connection strings, or just anything that's confidential that you ordinarily wouldn't want to have in a config file. And secrets are also versioned, so if you write the same secret twice with the same ID name, then you'll get a version history of it as well, which you can make use of. So let's go back and have a look at that. One of the key themes you'll see around here is that actually all of these sample applications are incredibly simple, which just goes to show that actually using this stuff is not that hard. Okay, so I'm going to create a secret called Stephen Haunts' secret. And I've got a very important string here that says Mary had a little lamb. So what I'm going to do is call set secret. Come on, internet, you can do it. Okay, so that's written that into the key vault. So from that, we get a URI back. So you might want to store that URI in a database. So if you know that you've got a specific set of secrets that you're storing, you can just store those URIs in your database and then retrieve them later. But what I'm going to do is I'm going to pass in my secret ID. I'm going to call get on it, and that's going to return my secret. Mary had a little lamb. So it's gone all the way out to a key vault sitting in the UK at the moment, and then it's come all the way back. So it's very simple to do. So the next trick we're going to look at is local key wrapping. Now, earlier on I said that generally encryption and decryption operations are going to cost you about 3 cents per 10,000 operations. So if you're working on a very large system, very high bandwidth or high volume system, you're probably going to start burning through money quite quickly. Even though it's only 3 cents per 10,000 operations, that can soon add up. But also we talked about the fact that doing the encryption operation on the HSM itself is expensive. So you've got the network hop over there, and then you've got the thing doing RSA, which is generally slow anyway. So what we want to do is you want to use a hybrid solution. So what we're going to do is we're going to create an AES key, which is 32 bytes or 256 bits. We're going to encrypt that with the HSM. Then that encrypted key we can then just go and store in our database. If that table ever gets stolen, then all it is encrypted. They need to get access to the keys on the key vault to recover that key. And then what we can do is we can do local encryption using AES, which is nice and fast, which means we're not doing any additional hops across the network. So let's take a look at that. The font on my screen has gone really small. I'm getting old, my eyes don't work. Okay. So this example is a little more complex, but it's not that much more complex. So first of all, I'm going to create myself a new key in the key vault. All of these examples are console apps and completely self-contained, so you can run each one independently. Okay, so we've now got a key ID for a key on the key vault. So what I'm going to do is I'm going to generate a random number using RNG crypto service provider, so I can step into that. And I'm creating a 32-byte or 256-bit key, which is the length of the key I need for AES. So now what I'm going to do is I'm going to take that key that I've just generated, and I'm going to encrypt it on the HSM. Just wait for the Wi-Fi to catch up. Anyone know any good jokes? Okay, I may have to switch to my backup plan. try this again. I've spoken at enough conferences now to know that there's a universal constant of speaking, and Wi-Fi never works when you want it to. So what I've done is I've created an abstraction called Fake Key Vault. What this is going to do is it's going to basically replicate the Key Vault operations, but locally. So I'm not actually technically calling out to the Key Vault at this point. I'm cheating, but it's just to illustrate the point. I knew writing this class would be a good idea. Okay, so I create a key. It's not actually created in the Key Vault. I've just created it locally, but I say it just illustrates the point. I create my AES key. I now encrypt that key using AES. So in this byte array now is a completely encrypted key. So I can convert that to a base 64 string, and I can just go and store that in my database because it's now protected. So we come along later, and we want to do some encryption and decryption in, say, a web API method. So first of all, to do that, we need to recover our key. So I'll make a call to the Key Vault, and I decrypt that key. So what I have in here is our unencrypted key. And because I'm using AES, I need to create what's called an initialization vector. That's just 16 bytes of entropy that you have to pass into AES. So now what I'm going to do is I'm going to encrypt a string there that says mega top secret stuff. I convert it to a byte array and I encrypt it with AES. I can show you what that looks like. So AES is stream-based in .NET, so you just create the stream, create the crypto stream, flush it, and then that's encrypted the data. So we now have a byte array with our encrypted data, and then we can decrypt it straight away. So if I convert those to text, again, hard to read, but that's our encrypted data up there. And then you can see where I've decrypted it below. So it says mega top secret stuff. Now you could go and do 1 million of these, and it's not going to cost you anything in Key Vault, because all we've done is we've done one decrypt operation to recover our key, and then we're doing everything else locally. So that's one way of reducing our costs on Key Vault and getting some performance benefits as well, so we're not constantly hopping across the network. Okay. So an example of where I've used this, so a company I worked for recently, we was building a software as a service claims management platform. And the way this platform works is it allowed insurance companies to basically come onto the platform as an additional tenant, and then their customers could then log on to their dashboards, which we provided, and then basically resolve their insurance claims for vehicles. So each tenant, because they were set up on the system, would have their own custom branding, so depending on which insurance company you are, when they logged into the system, it just looked like their sort of typical branding. So what we did when we do this, when we onboarded an insurance company, we would create a set of master keys in the Key Vault, so those keys belong to that insurance company only. And then what we did, every time we saved data into a database, anything that was sensitive or personal information, we would encrypt using this local key wrapping technique, so that even though all the insurance company's data was all stored together in one database, we actually had partitioning via encryption. So that looks something typically like this. So you've got the Key Vault and some app services and a bunch of databases. Each insurer has their own encryption key. So we've got insurer 1, 2, 3, and 4. So in the database, we had something like a tenant ID, which related back to the insurance company itself. And we had a key ID. And then we had their encrypted AES session key, which is stored in the database. But all of those keys were protected using the keys on the Key Vault. So the advantages of this end, as we said, local encryption operations are fast. AES is algorithmic by nature, and that's what computers are very good at. We only decrypt once from the Key Vault to recover our key, and we store that in memory. And this reduces the network hops, but also the other main benefit is it makes it easy to rotate keys. So you'll probably have in your company some security policies where you might say you have to change any master keys every 3 months. Now, if we was using those keys in Key Vault to encrypt all of our data, that would mean when we change that key, we have to re-encrypt everything in our databases, which is a nightmare. We don't want to do that. But in this instance, all we have to do when we change that master key is re-encrypt the one AES key. None of the other data needs to be re-encrypted because it's using the same key. Does that make sense? Cool. Got ahead of myself there. So you only need to re-encrypt the AES session key. So you get a lot of performance benefits from that. So So the next one is key versioning. Now, changing keys over time is important, as we just said. You might have security policies that mandate that you have to change your keys every so often. If not, then you need to have a word with your security people, because that's kind of a good practice. And really, this is kind of like the digital equivalent of changing your locks on your house. You know, if you ever get any kind of breach or any suspicions, you change all your master keys, just like you do with a house if someone tries to break in. And the example we've looked at here is, you know, as we've done local key wrapping, we created the key in the key vault. All keys are versioned. So we've got key version 1.0, and we use that to encrypt our AES session key. But then, 2 months down the line, we might decide to rotate that key. So we have key 1.1, which means we can retire the existing version of the key, and then we just re-encrypt our session keys. So that's typically how that might work. But also, we can have the idea of incremental keys, or rolling keys. An example where I've done this is one company, we built a PCI DSS card vault for storing credit cards in a protected network. And the way this works is we'd have key version 1, and then we might have a policy that says for every 500 cards that comes in, we're going to change the key. So the first 500 cards we encrypted with key version 1.0, the next 500 might be with key version 1.1. So it's just an example of using rolling keys. It's just another way that you can do it. So let's go and look at another demo. Oh, don't actually have a demo for that bit. I put that slide in by mistake. Moving on. So the next bit I want to talk about is password protection. So, you know, passwords aren't great. They're kind of a crappy way of authenticating your systems, but they're here to stay because it's easier for our end users to remember a password. Oh, how annoying. Okay. So let's go through some of the options. So obviously the worst situation is plain text passwords. I think we can all agree that that's bad. You don't want to store plain text passwords in our database. The next one that people might do is to store just a hashed password in the database, you know, using like a SHA-256 hash. Does anyone do that currently? Store hash passwords? One person? No one, two? Okay, no one else is admitting it. But this can be a problem. So if you store a hash, say a SHA-256 hash password, it's susceptible to brute force attacks and rainbow table attacks or dictionary attacks. And what this means is that you can have massive pre-computed dictionaries of passwords and their hashes, which actually makes it very easy to reverse. So I've got an example here. This is a website called crackstation.net, which you can go and have a play with. So in the grey box at the top there, we've got a SHA-256 hash. You know, you put your capture code in, hit the button. It works out that it's a SHA-256 hash and that the password was secret69. Now you can actually go and download the password table used by this site. It's sort of several gigabytes in size. But reversing plain hashed passwords is actually quite simple. So if you use tools like Hashcat, you can sort of do it in seconds. So the next option then is to use a salted hash. I'm one step ahead of you. So a salted hash is where you add an additional piece of entropy onto your password before you hash it. And that could be, you know, a randomly generated number that's 32 bytes in length. Does anyone do this currently? This is sort of more common. So you have a password, you have your salt, and the salt you need to store somewhere because you have to have that salt to recover the password or to create the same hash of the password. You pass both those into your hashing function, and then you get your hash password out. Now this is better than just doing normal hashed passwords, and at the moment it's probably very secure. But the problem is, as GPUs and CPUs are getting faster, tools like Hashcat can start crunching billions of these per second, and that's only going to get faster. So what might be a protected salted hash password now, in 5 years' time, could be compromised, or maybe sooner. So there's another step we can go, and that's to use what's called a password-based key derivation function, or something called bcrypt. So is anyone using either of those? Cool. So this is very similar to a salted hash password. So you have your password, you have your salt, but you also pass in a number of iterations. And what this does is it repeatedly hashes that password and then gives you the resulting password hash. And the idea behind this is you are trying to programmatically slow down the hashing process. So depending on what that number of iterations is, you could stop Hashcat from doing billions of calculations per second down to maybe doing 5 or even less, depending on your iteration factor. So what we're trying to do is we're trying to defeat Moore's law. So as processors get faster, we're trying to slow the process down. Now in .NET, this is incredibly easy to do. You just need those few lines there. So we've got a class called RFC2898 derived bytes. I'd love to meet the person who names these classes at Microsoft. You pass in your password to be hashed, you pass in the salt and a number of iterations, and you get the hash back out the end. So we look at some example timings. So, 100 iterations might take 2 milliseconds, 1,000, 16 milliseconds, all the way up to 500,000 iterations, which might take, say, 7 seconds. So it just goes to show that, the more iterations you put in, the slower it's going to be. Now, as an application designer, you need to think very carefully about what's an acceptable trade-off for your site. So you might notice on some websites where you log in and it might feel like it takes a couple of seconds before anything happens. That's probably because they're doing something like this or bcrypt behind the scenes. But you need to work out what an acceptable level is. So technically you think, oh, we're good, use a password-based key derivation function. Why are we even mentioning this in a Key Vault talk? But there is an additional trick that we can do using the Key Vault to protect some of our passwords, or certainly some of our more important administrator passwords. So this is what we've currently got. A password, assault, and iterations. But then what we can do is we can do a hash message authentication code, which is an additional hash of that password. And the way hashmacks work is you have to provide it an encryption key, as well as the password to hash, which means that anyone else who wants to calculate the same hash has to have a copy of that key. So what we're going to do is we're going to get that key and we're going to do local key wrapping like we did before. So we can store that key in our database, but it's encrypted. So hashmacks are very straightforward in .NET. You just create this hashmack SHA-256 object, pass in the key, and then you can compute a hash. So it's very easy to do, but because we're protecting that key using the Key Vault, we get a lot of additional benefits. So let's take a quick look at that. Okay, so I'm creating myself a new key again. Hopefully it will work, or I'll have to switch over to my fake Key Vault. Okay, the Wi-Fi's not playing ball. I'm going to cheat. Just pretend I'm using the Key Vault and we're good. So I create my key, and then I create a new local key, just like we did before. So 32 bytes is our key. And I now encrypt that using the Key Vault, so we can go and store that in a database because it's encrypted. So now what we're going to do, I want to set a new password. So we have our password here, which is password, where I've changed some of the letters to numbers to make it really secure. I generate a salt, which is exactly the same as generating a key. It's just a random number that's 32 bytes in length. And then I'm going to use the password-based key derivation function with 20,000 iterations. I'm just going to hash that password. And we call get bytes, and we pass back 20 bytes. The reason we pass back 20 bytes is because behind the covers, this function uses SHA-1, which ordinarily you wouldn't use for new code, but that's what this algorithm uses. So it's doing 20,000 iterations of SHA-1. But SHA-1 returns 20 bytes. That's why we're calling get bytes 20. So that's what we're kind of used to doing. That's our password-based key derivation function hash. Try saying that 10 times faster. So typically that's what we might ordinarily store in a database, but now we're going to go one step further, and I'm going to create a hashmacks of that password using that decrypted key, which we covered earlier. So if we try and look at our console window, well, that's small. So you can see our initial hashed password at the top. You can see it's quite short. But then because we've rehashed it using that hashmacks, using our protected key, it's actually created a longer hash because it's using SHA-256 internally. So we've actually got a longer, more secure hash off the back of it. Okay. So this gives us quite a few benefits. So if your password table is ever stolen, and it's quite common for people's password tables to be stolen these days, if they want to try and recover or work out what that password is, they've first got to recover the hash map first, but they can't because it's using a key that's protected by your key vault. So, but even then, if they ever did manage to get past that, they've then got to try and break the iterated hash behind the scenes, which could take them quite a long time to do. So this makes dictionary and rainbow table attacks virtually impossible at the moment. Now, you might not use this technique for every single user on your system. You might just want to reserve it for admin accounts or important accounts. That's kind of an application and security decision that you have to make in your company. But it's quite an interesting technique just to add that extra little layer of security on top of your passwords. So the last bit I want to talk about is digital signatures. So this is kind of like the last of those 4 pillars that we talked about at the beginning. So a digital signature is a mathematical technique used to validate the authenticity and integrity of a message, software, or digital documents. Has anyone used a website like DocuSign or any of the equivalents that are out there? Yeah, so effectively, services like that are doing digital signatures of documents. You might upload a contract for something, so you might be buying a house or signing a new employment contract. You'll go on there, you'll say that you're happy with it, and it creates a series of digital signatures. So that further down the line, you can't turn around to the originator of the signature and say, you said you're going to pay me 10,000 euros, not 5,000 euros. You can't go back and deny what was in the contract, it's been digitally signed. So that's kind of the same concept of what we're going to do in code. So there's 3 parts to digital signatures. We need a way of creating keys. Well, luckily we've got the Key Vault for that, so we've been using that all through the talk. We need a signing algorithm and a signature verifier algorithm. Now, digital signatures, or certainly the ones in .NET, are based on RSA. Now, as you said before, RSA has limits in the amount of data that you can encrypt and decrypt in one operation. You can't encrypt data larger than the size of the key. So what we do is when we create digital signatures in .NET, we have our original data at the top there. We first create a hash or a hash map of that data, and we then create a digital signature off of that hash, is typically how it works. So if we look at my amazing artwork at the top here, so we've got a Bob at the top there. Now, the way digital signatures work is kind of flipped around from how RSA encryption works. In normal RSA, you encrypt using your recipient's public key, then they decrypt with their private key. Digital signatures, it's the other way around. So you create the signature using your private key, and then the recipient verifies the signature using your public key. So we've got Bob here. He uses his private key to create a signature. He sends it over the internet, or the big spider's web. And then down the bottom, she uses Bob's public key, because she has access to his public key, because it's public. And she uses that to verify the signature, and that will return either true or false. True if the signature is intact and hasn't been modified, or false if it's been tampered with. Now, if we was going to do this by hand in .NET, we would use classes like this: RSA PKCS1 signature formatter and signature deformatter. Like I said, I'd love to meet the person who named these classes, because they're amazing. It's very common that you might just miss these in the documentation, because they've got such arbitrary names that people just tend to skip over them. But luckily, we don't need to use those, because we have digital signature functionality available in the Key Vault, which is what we're going to use. So let's go over to the last demo of the day, or of this talk. Now, because I've had problems with the internet and we're getting low on time, I was going to go straight to the fake Key Vault, because the internet's not been working too well. So literally all that's doing is I'm just doing the digital signature operations locally, so I'm kind of pretending to be the Key Vault, but you'll kind of get the principles. If you download this code and you want to use it, just remove the word fake from there, so it says Key Vault, and it will use the real hardware. So let's go in. Okay, so first of all, like before, I'm going to create an encryption key in the Key Vault. Oops, hold on. Okay, so we created our Key Vault key. So now we have a document. In this case, it's just a piece of string or a string, but it could be a file, it could be pretty much anything that you turn into a byte array. So first of all, what I'm going to do is I'm going to create a SHA-256, just a standard hash of that document first. So just a few lines of code to do that in .NET. Then what I'm going to do is I'm going to make a call out to the Key Vault. I'm going to give it my key ID, and I'm going to give it that hash that we just created. That's going to create our digital signature for us. So now what I want to do, you sent your data and your digital signature to various recipients, and now they want to verify that the signature and the data that have been sent is valid. So what they do is they call verify on the Key Vault, they pass in the key ID, the document digest, which is the signature we just created, or the hash of the data, and we pass in the signature. Now in this case, because we haven't tampered with the data, it should return true. So we know that that signature matches the data. So let's just do it again. So again, I create my key, I create a hash of the data, I create my signature. Now we're sending it to our recipient, but I'm a malicious third party who's managed to intercept the data. So what I'm going to do is I'm going to mess around with the original SHA-256 hash. So I'm just going to change just one of the bytes there. So now when we call verify, passing in our dodgy hash and our original signature, it will come back and say false. Okay, down to the last few minutes. So we started off by talking about, the problems of data breaches. They're not getting any better, they're getting worse, but we should just learn to live with that now. I think it's the best policy. And we want to, data breaches are inevitable, so it's not if they're going to happen, it's a case of when they're going to happen. So to help get us around these problems, we've discussed using Azure Key Vault, which is a software abstraction over hardware-software security modules provided by Microsoft, which makes using HSMs very cost-effective to use. And we discussed that they're based on this piece of hardware here, which is the Thales Shield, a very expensive piece of hardware, which Microsoft has kindly purchased on our behalf. Setting the Key Vault up is very easy. As I said before, you can just Google the documentation, but the instructions that Microsoft provides are actually very good. And then we looked at different patterns. So we've got multiple environments, configuration of secrets, local key wrapping and key versioning, password protection, and digital sign-in. And as you've seen from the code, a lot of these things are actually very simple to do. And again, there's the code if you want to get it. If you want some more information, and this has kind of tickled your fancy on key vaults and encryption, I've got 2 Pluralsight courses that might help you. One's Enterprise Data with Azure Revealed, which I recorded with my good friend Lars Klint. Kind of talks about some of the concepts on Key Vault. Another course I've got called Practical Cryptography in .NET, which takes a deep dive in how to use all the crypto primitives and how to use them all together in .NET. Also perfectly valid for .NET Core, now we've hit version 2. And if anyone's interested, my latest course is called Blockchain Principles and Practices, which is all about, this course takes you through how to build a blockchain from scratch in .NET, just to show you how the principles behind it. So, I write some books in the Gentle Introduction series as well, which you can find on Amazon. Little shameless plug there at the end. But thank you very much. It's been a pleasure to come over to Poland and speak to you all. Thank you very much.